Dear students, continuing with the chapter of forced vibration, today's lecture is on the topic displacement transmissibility due to support motion. I, Dr. Balraj Singh Brar from Yadavindra College of Engineering, Talwandi Sabo, India, am presenting the lecture. We have to now derive the relation for absolute vibrations of a mass due to support motion. Let there is a mass m supported by a base through a spring having stiffness K and a dashpot having damping coefficient C. Let the base is subjected to a vibration which is following the profile and it is denoted by Y. Y is B sine omega t, where B is the amplitude of vibrations of base about an equilibrium position and omega is the angular frequency of vibration of the base with time t. Because of the base vibration along the vertical axis, the mass will also vibrate about an equilibrium position. Let when the base is at a position y, from equilibrium position, the mass is at a position x. Now we have to find out the relation for x. And still the mass is moving away from the equilibrium position with the velocity x dot. Now we will observe the movement of mass m on a plotter with the help of a stylus. Now the plotter's axis is attached to a common datum, which is the reference for base as well as the movement of mass. So basically this plot which we will get is absolute motion of the mass and is governed by equation of x, which is to be determined in this topic. Now let us draw the free body diagram of mass m. Now this is the mass m. It will be subjected to a spring force, which is stiffness of spring multiplied by relative displacement of mass of this point attached to mass to this point which is attached to the base. Say x is greater than y, then x minus y will be positive and this spring force will be acting downwards. Similarly, the relative difference between velocity of point which is attached to the mass x dot minus base velocity y dot. So this relative velocity multiplied by c gives us the damping force. This, if x dot is greater than y dot, then also this is opposing the movement. Let this is the case. Now according to D'Alembert's principle, if we apply inertia force, which is mass into acceleration mx double dot, in a direction opposite to the motion, in opposite to the direction of motion, in this case it is x dot. So let us apply inertia force in a direction opposite to x dot. So this is mx double dot. So this will bring this body in static equilibrium. Means with all the forces marked on the free body diagram of mass m, now for these forces the body is in equilibrium. So simply means inertia force mx double dot plus inertia force mx double dot plus damping force c into x dot minus y dot plus spring force k into x minus y is equal to 0. So this is the differential equation of motion of x with the time t, which is to be solved to find out the relation for x. Now we have derived the differential equation mx double dot plus cx dot minus y dot plus kx minus y is 0. Now in this, y is the equation of base motion or vibration, which is a simple harmonic motion governed by equation b sine omega t, where b is the amplitude of vibration of base and omega is the angular frequency. Taking derivative of y with respect to time t, we get velocity of base at any time t is given by relation y dot is equal to minus omega b cos omega t. Now we put the value y in this differential equation here and y dot here, and when we solve this, the relation will be mx double dot plus cx dot plus kx is equal to y term we have taken to the other side, so it is c omega b cos omega t, and is another term is spring term is kb sin omega t. Taking b common, we get the equation mx double dot plus cx dot plus kx b times square bracket starts c omega cos omega t plus k sin omega t. Now we have to put the values of c omega and k in terms of an angle alpha. So focusing on the triangle, this triangle on the right side, say this is A, this is B point, this is C point. Now C omega is the height of this perpendicular and K is the base, then hypotenuse will be square root of C omega square plus K square. So from this relation we know base by hypotenuse is equal to cos alpha. So base is equal to hypotenuse square root of c omega square plus k square into cos alpha. And similarly the height c omega is square root of c omega square plus k square hypotenuse times sine alpha. Now let us put the values of k here and c omega here. When we put this value, what we get is c omega again hypotenuse times, so hypotenuse will be common, or the equation will be mx double dot plus cx dot plus kx is equal to b times b multiplied by hypotenuse, which is square of c omega square plus k square. Inside is sine alpha cos omega t, cos alpha sine omega t. So basically this term, square bracket term, is sine omega t plus alpha. So we get the relation differential equation in the form mx double dot plus cx dot plus kx is equal to b times under root of k square plus c omega square sine of omega t plus alpha. So differential equation has been modified for our problem. Next, from this triangle, tan of this angle alpha, tan alpha is perpendicular by base c omega by k. So we get tan alpha is c omega by k, or alpha is tan inverse of c omega by k. Now c omega by k we can write in terms dividing and multiplying with cc, which is critical damping, c by cc into cc by k into omega. Now this term c by cc, this becomes zeta damping ratio, and the critical damping coefficient value is 2 times √km. Now when we solve this term, this term under root km by k, it becomes under root m by k, which is the natural inverse of natural frequency. So omega by omega. Now this relation, by putting the value of c omega by k, we get alpha to be tan inverse of 2 zeta omega by omega n. Now we know the differential equation in terms of an angle alpha has been introduced, and alpha's value is tan inverse of 2 zeta damping ratio of the system to multiplied by omega n frequency ratio. Now moving ahead, carrying these differential equation and alpha relation forward, we have carried mx double dot plus cx dot plus kx is b times under root k square plus c omega square sine omega t plus alpha, and alpha is tan inverse of 2 zeta omega by omega. Now we know differential equation of forced vibration is of the type mx double dot plus cx dot plus kx is f naught sine omega t. When we compare this equation of forced vibration with this equation of sport motion, we observe that f naught is equal to this term. This is f naught. So f naught is equal to b times square root of k square plus c omega square. And in place of angle omega t, here the angle is advanced by an angle alpha, and a new angle is omega t plus alpha, and alpha's value we know. For the equation of forced vibration, the solution, steady state solution, once the transient vibrations have vanished from the system, then the solution is only particular solution, we have discussed in the previous lectures, is equal to a sine omega t minus phi. Means now the system mass will vibrate with a amplitude and will be lagging behind the external excitation by phi. And we have already derived in previous lectures a is equal to f naught by k, and in the denominator is square root of 1 minus omega by omega n square, this whole term is square, plus 2 zeta omega by omega n, this term is square. And phase difference phi is tan phi 2 zeta omega by omega n in numerator to 1 minus omega by omega n square in the denominator. This differential equation and this differential equations are same. Only thing is this amplitude got modified, but all terms are constant terms, and this external excitation is advanced than force vibration by an angle alpha. So for this, the solution, steady state solution, will be also equal to the particular solution, because complementary function has vanished from the system, transient vibrations have died out. So similarly the solution will be a, amplitude of vibration will be a sine omega t plus alpha minus phi, or we can write minus phi minus alpha. So new phase difference is phi minus alpha, and a is the amplitude. So from again the same relation for the force vibration similarity, we substitute value of f naught, which is b square root of k square plus c omega whole square. When we take k inside, we will be modifying it, and from this relation similarly we get relation for phi, which is tan inverse 2 zeta omega by omega n to 1 minus omega by omega n whole square. So what is in the summary? For this differential equation, solution will be of the type this: a sine omega t minus phase difference of phi minus alpha, where phi will be given by this relation. Damping ratio is known, frequency ratio is known, frequency ratio is known. And alpha is given by this relation, tan inverse of again 2 zeta, damping ratio is known, frequency ratio is known. And this amplitude A is b and root k square plus c omega square by k to the denominator term square root of 1 minus omega by omega n square, this whole square plus 2 zeta omega by omega n, this term's square. Now we know the solution. Only thing is, for simplification, we will modify this relation of A in the coming slide. So, for this differential equation as discussed, solution is this. Particular solution, steady state solution is A sine omega t minus phase difference phi minus alpha. Phi is known, alpha is known. We can substitute values of phi and phi here to find the solution, and alpha here to find the solution. Only thing is determination of A. A is this, but we don't put in this terms. So what we do, when we take k inside, the numerator here becomes 1 in the square root terms. Here is c omega by k whole square. Now we have already solved. C omega by k is equal to 2 zeta omega by omega n. Let us substitute it here, and denominator term remains the same. And let us take b here in the denominator. Then the solution is of the type a by b is 1 plus 2 zeta omega by omega n square to square root of 1 minus omega by omega n square, this term's square plus 2 zeta omega by omega n square. So complete solution, x is equal to a we can find out from this relation, ratio of a amplitude of mass to b amplitude of base movement, which is given by this. All terms are known. This ratio is also known as displacement transmissibility. So we have derived the relation for displacement transmissibility, which is defined as ratio of amplitude of mass to the amplitude of base. And here again to the solution, x is a is known, sine omega t minus phase difference is phi minus alpha. Phi and alpha are calculated from this. Now again, this is the diagram of the system. Mass with support movement. Support movement is y is b sine omega t. Say this is the plot of y with respect to time t. So it is vibrating with an amplitude b, and omega is frequency. So this time period is equal to this t. So time period for both base and mass will be same. It will be 2 pi by omega. Only thing is, when base is vibrating, mass will also vibrate, and absolute vibrations have been noted, governed by equation x is a sine omega t phi minus alpha. So this will be the solution. A is the amplitude of vibrations of mass, absolute movement of mass with respect to common datum. Time period is same, as for the base movement, and phase difference is phi minus alpha relations we had derived in the previous relation. Now only thing is, because in real life problems we want, whether it is a suspension system, design of suspension system problem, we want that base may be vibrating, which is usually taken as the chassis of the vehicle to which wheels are attached, and it follows certain profile due to the road profile and the velocity. The mass should, body is the mass, should vibrate with lesser amplitude. Means we want that B, from B amplitude of base, A should be practically lower. Similarly, second types of problems, let mass M is an instrument, base is vibrating, we want to isolate this instrument from the base with the help of a stiffness element and damping element. Then we want to again control A should be very less, A amplitude of mass should be absolute, amplitude should be very less with respect to B. Means we want to isolate the vibrations from base to the mass. So for both of these problems, relation of displacement transmissibility A by B is equal to 1 root of 1 plus 2 zeta omega by omega n square by, in the denominator, square root of 1 minus omega by omega n square, this whole term square plus 2 zeta omega by omega n square will be made use of, and we have derived the usage of displacement transmissibility relation of sport motion. This is a relation for absolute motion or vibrations of mass with due to the vibrations of sport. As discussed, displacement transmissibility A by relation we have derived, and this is a summary for my dear students. Use this displacement transmissibility or simply transmissibility A by B relation to solve the problems or in the designing of automotive suspension systems. Second, this relation A by B is used in the problems of vibration isolation, and here it is a relation for displacement isolation. Even for force vibration we will later on derive the relation, though the transmissibility ratio is given by TR, but relation will be again luckily coming to be same for solving our problems. So kindly remember usage of A by B, which is displacement transmissibility relation, is in the design of automotive suspensions and in the isolation problems. Thanks, my dear students.